Hey everyone! The focus of today's lesson is the basic structure of an atom. And for most of you guys, this is something that you've probably covered in some detail, at least, in previous science classes such as physical science. And so you began today by watching a video that kind of detailed some of the history behind how the model of the atom was developed. And so what we saw is that over many years and over many scientists working in different countries with different languages, different cultures, that through different experiments, they were able to discover a better picture of what the structure of the atom is actually like on the inside. And so it started with Democritus and kind of led up to some of the more modern day atomic theory with Heisenberg, so on and so forth. And so normally, if we weren't so pushed for time with a late start to the school year and also kind of several testing days in October, we would normally have an opportunity to look more at some of the experiments, such as the cathode ray tube, the gold foil experiment, some of those that were actually used to arrive at different conclusions about what the atom looks like. And so that's one takeaway that I'd like y'all to have from the video, is that the results from the experiments led to conclusions about what the atom was like. And as they would do new experiments and gain more data, that gave greater insight into the structure and the design of the atom. And so essentially, we're just going to take a couple of quick notes on just some of the basic features that will be most helpful to us in this introductory chemistry class. And so by definition, what an atom is the smallest unit of matter that still maintains its properties. And so once you get down to an atom, that's kind of as far as you can go in order to still maintain the same properties of a substance. It still maintains its properties. And so every atom of gold, for example, would have the properties of gold. It would maintain it. But if we tried to get smaller, things would start being a little bit different. Now, within an atom, we do have smaller particles that make it up. And those particles are referred to as subatomic particles. Sub being beneath, so it's kind of beneath the atom structure, or within it rather. And those three particles are protons, neutrons, and electrons. And so I've got just kind of a brief illustration here. And so the protons and neutrons are found located within what's called the nucleus, which is located at the center of the atom. And that nucleus is crazy small. But because all of those protons and neutrons are packed within it, it leads to that nucleus being extremely dense. Now, the electrons, on the other hand, are very small, and they're kind of located more on the outside of the atom in what's called the electron cloud. And we'll learn later that the electron cloud really consists of what are called orbitals. And so just think of for now, think of the protons and neutrons as being packed in the middle in the nucleus, and the electrons kind of on the outside in what's called the electron cloud. Now, for symbols, the symbol we'll use to represent a proton is a P with a plus sign. And that's because the proton has a charge of +1. The neutron, kind of like the name sounds, has a symbol of just N. And that's because its charge is 0. It's a neutral particle. The electrons have a symbol of E- because their charge is -1. Now, we already talked about a little bit where these are located within the atom. Both the proton and the neutron are located within the nucleus, while the electron is located kind of around the outside of the atom in what we're going to call, for now, the electron cloud. And that's a good general term to stick with. Now, in terms of relative size or relative mass, the proton and neutron are about the same, and they have a mass of about 1 AMU, which stands for atomic mass unit. So out of the three particles, the protons and neutrons are larger. Now electrons are just very, very small. So small that their mass becomes insignificant when compared to the mass of the protons and neutrons. And so we're actually going to find that when an atom's mass number is calculated, it's going to be based on the protons and neutrons, because the electrons are so small that adding in their mass wouldn't make a big difference. Now, because of this fact, the protons and neutrons, they are the ones that overall contribute the most to the mass of the atom. Because they're so densely packed inside the tiny nucleus, they don't really affect the volume much, but just the mass. Now, electrons, being on the outside in that electron cloud, they do contribute more to the volume, or the overall size or radius of the atom. And so those are our three basic parts, or subatomic particles, within our atom. Now, there are a few different terms we can use when referring to these subatomic particles within an atom. The first of those terms is what's called the atomic number. And so essentially, the atomic number is just the number of protons in an atom's nucleus. And so essentially, the atomic number is what makes something an atom. Now, on the periodic table, this number of protons, or atomic number, is going to be located at the top of the periodic table. So for example, if you look at hydrogen, we'll just kind of start easy. There is a 1 above him on the periodic table. That is his atomic number, and that means that hydrogen has 1 proton. If you were to look at helium, He, you would see the number 2 on top of him. That means he has 2 protons. And this is what gives the identity to an atom. So that means that every single atom of hydrogen has 1 proton. Every atom of helium has 2 protons. And so I'm going to make a note of this, that this is tied into identifying an atom. Or we'll say identifies an atom. Now, mass number is another useful term when talking about atomic structure. And so what mass number is the number of protons plus the number of neutrons. Again, those are the most massive particles within an atom, so they contribute most to the mass. Now, a big note here, and this is something we kind of have to break this misconception. Unfortunately, it's taught sometimes in 8th grade physical science. But anywho, the mass number is not on the periodic table. Only the atomic number is shown. So if you're ever looking for mass number, it's something that you have to calculate by adding the protons and neutrons. You can't just look it up on the periodic table like you can atomic number. So we'll make a note of that. The atomic number is the top number on the periodic table. While mass number is not found, it must be calculated. Now, when you take these two terms, there are different notations that you can format them in. The first type of notation is what's called nuclear notation. And so your chemical symbol, which is your letter code from the periodic table, is written. Then, to the left, your mass number goes on top, and your atomic number goes on bottom. So here this is representing helium, which has a mass number of 4, and an atomic number of 2. Now, a second form of notation that's used is sometimes called hyphen notation. Now, in hyphen notation, the only number that's shown is the mass number. So you either write the element name with a dash followed by the mass number, or you can use the abbreviated element symbol dash, then the mass number. Now, the reason they don't have to give you the atomic number is because you can easily look it up from the periodic table. And so when working kind of these next practice problems, you'll want to make sure to have a periodic table nice and ready. So let's go ahead and practice kind of filling out this chart, if you will, which kind of helps us make sure that you can identify how many of each subatomic particle are present within an atom. And then we also have some practice representing them in different forms of our notation. Now, one thing that's going to be helpful to note is that the number of protons will be equal to the number of electrons when the atom is neutral. And so since protons are positive, if an atom has 3 protons, we should assume that it would have 3 negative electrons in order to balance out and make the atom neutral overall. So if you're told to assume that an atom is neutral, then the protons will be equal to the number of electrons. And that's what we're going to do here for our basic practice, is just assume that these atoms are neutral. All right, so let's go ahead and work a few of these together. So what we have is kind of a chart, and it starts off with atomic number and mass number and kind of works its way to the notations. And so I'm going to kind of talk you through how to think about each of the blocks. So remember that your atomic number is this, by definition, the number of protons. So your atomic number and number of protons column should always have the same amount. Now, when it comes to number of neutrons, that's something that we're going to have to calculate from the mass number. If you'll remember that the mass number is protons plus neutrons. That's kind of one thing together. Now what we need to do to be left with the neutrons is we should subtract off the protons. So it's convenient, we've got our protons right here. So if we do protons plus neutrons minus the protons, that will tell us just the number of neutrons left over. That would cancel out our protons. So here in this case, 40 is the sum of the protons and neutrons. So if we subtract 20 protons, that tells us that the atom has 20 neutrons. Now we're ready for our electrons, which is based on this statement here. We're assuming that all of the atoms are neutral. So that means the number of protons must be equal to the number of electrons. So that is 20 as well. So now what we need to do is go to our periodic table and look up, well, which atom is number 20, and that will let us get the symbol for our element. So let me pull up my periodic table right quick. Sorry, forgot to have it pulled up. Here it is. All right. Trying to find one that's relatively clear. All right, this one's pretty easy to see. Okie doke. So here we have it. We're looking for element number 20, and that happens to be Ca for calcium. And we'll kind of work on, as we go throughout these next several lessons, kind of better learning what element symbol goes with an element name. So it's going to be calcium. And so the symbol is Ca. Now here they already have the hyphen notation filled in for us. Remember that in hyphen notation you have the element name followed by the mass number. Now it's up to us to fill in the nuclear notation. So we start with the element symbol, which is Ca. On top we should place the mass number, which is 40. On bottom, we should place the atomic number, which was 20. And there is our nuclear notation. Let's go ahead and try the next one as well. And you'll notice they give you different information each time. So on this one, they've given us the mass number as well as the nuclear notation. So let's start with our nuclear notation since that gives us more information. So what this tells us about oxygen is that the mass number is 17 and the atomic number is 8. They've already filled in the mass number for us, so let's go ahead and fill in the atomic number 8. We know that by definition, the atomic number is the number of protons, so I should also have 8 protons as well. Then, I need to calculate my number of neutrons. So what I can do is take my mass number of 17 and subtract my atomic number of 8. That works because mass number is the sum of protons and neutrons. So if you subtract the protons, it leaves you with the number of neutrons, which is 9. So 17 minus 8 gave us 9. Now we want to work with our number of electrons. Again, we're just assuming that these atoms are neutral. So if that's the case, the protons, which are positive, should be equal to the electrons, which are negative. So 8 protons should equal 8 electrons. Our symbol for the element they already gave us was the letter O, and now we need to do hyphen notation. The symbol for, or the element for O is oxygen, and in hyphen notation we only show the mass number, which is 17. So oxygen dash 17 will be our hyphen notation. All right. So now what you'll do is you'll practice kind of these next 1, 2, 3, 4, 5, 6, 7 rows on your own and really get a sense for, hey, am I understanding how to obtain the information for each of these values? If not, make a question of it and then message me about it or come see me in office hours. And so what I'd like you to do is kind of spend a few minutes on this, and if you'll pause the video while doing that, then I'm going to pop up the key, that way you can check yourself. Now again, you've got to try this on your own first. If you do it based off the key, that's going to give you a false sense of understanding. So pause the video, give it a good try, and then I'll let you check yourself and we'll go over this last box here. All right, welcome back, and thanks for practicing. So here's the key. Again, you can pause the video long enough for you to check your answers. Again, be diligent, make note of any questions that you have, that way you can get them answered. And then I'll go to this next thing here in just a second. All right. So the last thing is kind of an introductory term, if you will, for the next topic on our list, which is called isotopes. Now, what we're going to find is that isotopes are atoms of an element with the same atomic number but different numbers of neutrons. And what happens is if the number of neutrons changes, so will the mass number, since it's the sum of protons and neutrons. But different numbers of neutrons, which results in a different mass number. And so if we look at some of our examples here, we have 3 different isotopes of hydrogen. Now you'll notice that what stays consistent is they all have 1 proton. That's what makes something a hydrogen atom, is 1 proton. That's its atomic number. But what changes is the first isotope of hydrogen has 0 neutrons. The second isotope has 1 neutron, and the third isotope has 2 neutrons. And so what we see is that changing the number of neutrons is going to change the mass number. So you have hydrogen 1, hydrogen 2, and hydrogen 3. Now, it's still hydrogen, it's just a slightly different form because you have a different number of neutrons within the nucleus. Same thing here with lithium, where consistently they have the same atomic number of 3 protons, but we'll notice that their mass number changes as they add an additional neutron each time. So that's just something to be on the lookout for and to remind us that by definition, The atomic number or number of protons is what makes an atom an atom. Sometimes the number of neutrons will change, and we'll see that sometimes the number of electrons will change as well. But as long as the protons are consistent, you do have the same atom. If the neutrons change, you form what's called an isotope. Alright, so thanks so much. We'll see you for the isotopes lesson next.